Yeah, so here's just a nice drone shot of our test site with our research barge and BladeRunner deployed and College of Fisheries doing fish sampling and a big old tree having come down. And this one we probably avoided by pushing ourselves with our motorboat on our mooring line. But yeah, that's the kind of thing we are running into at the test site. Uh, There we go. Funding acknowledgement. All this work is under ARPA-E Sharks program. And I'll run quickly through sort of UAF's research motivations. I think a lot of folks on this call will be familiar. Talk briefly about kind of BladeRunner Energy's technology and origins and how we came together on a Sharks proposal. And then I'll kind of walk through what this iterative R&D at the Tanana River Test Site has looked like, things we've learned, things we've done, some results. Then I'll talk about kind of more recently work we've done with NC State, which is developing a microgrid controller under an ARPA-E Open Award and kind of how that came together. I've got a slide on reflections, and if we want to hold Q&A until after the recording, we can do that. And then I'll talk briefly about kind of next steps where this project is going. On the left, so ACEP, our research group, exists to do applied research for technologies relevant to remote Alaska communities. And on the left, we have the results of a 2014 resource assessment at a whole bunch of riverine communities, and the big orange bars are the hydrokinetic resource in the river in the summer, and then the little blue bars are the average electrical load. So there's this immense resource adjacent to these remote microgrids. And the top right was an early turbine deployment in Ruby, Alaska on the Yukon, and it jammed up with logs. And that was really the motivation for establishing the research group at ACEP, looking at hydrokinetics and building out the Tanana River Test Site in Nenana. And so this is just an overhead view of our debris diverter, which we sometimes use, sometimes don't, increasingly don't use with BladeRunner, the research barge that we deploy turbines from and collect data on, and then downstream of that, the fishing system. So the College of Fisheries and Ocean Science is always doing fish sampling to look for adverse impacts. So BladeRunner Energy, they started, one of their founders is Moriel Arango, who's a UW grad and a PMAC alumni. And they were looking at developing small-scale turbines for irrigation canals. So this is a picture on the right from some of their early testing. So pretty small-scale system, shallow water. They were looking at biomimicry in the rotor, mainly to avoid entanglement with grasses and weeds and stuff like that. But ACEP, we became aware because they engaged with us to do some market research on remote Alaska applications. And when I saw their turbine with these swept leading edges at the end of this sort of flexible torsional cable behind a generator housing, I thought, man, that gets the generator out of the water. The compliance in that drive shaft could help the rotor absorb debris impacts, and those curved leading edges, they're already seeing that they don't entangle with grasses and weeds. Maybe that would extend to sticks and the kind of debris we see in our rivers here. And shortly thereafter, the ARPA-E Sharks program was announced. Submarine, Hydrokinetic, and Riverine Kilo-megawatt systems. And something that was really interesting about the ARPA-E Sharks program was their use of this metric space to evaluate proposals and technologies. And so on the right is the graph from their evaluation spreadsheet, but basically you have a metric of annual water to wire efficiency. So it's basically conversion efficiency and capacity factor and rotor efficiency, the product of those on the x-axis as metric 1. And then on the vertical axis, metric 2 is structural cost efficiency. And essentially it boils down to what is the cost, the CapEx per unit swept area. And they basically convert it into an equivalent mass of steel. So if you use something that costs twice as much as steel per kilogram, you multiply the weight of that item by 2, and you get an equivalent mass of steel. So it's meters squared per kilogram. And what you end up with is these LCOE ISO lines. And so any point along these curves is an equivalent LCOE, and then those curves can shift up and down depending on the OpEx, and so the operations and maintenance cost. And so they had four sort of scenarios, four applications, and we targeted the S1 scenario of remote riverine. And so basically, you're trying to get a system that is above the dash line and obviously doesn't exceed the vertical line, which is the BETS limit. So you kind of have this design space that you're trying to get your design into. And so our proposal with BladeRunner Energy proposed to increase M1, the conversion efficiency, by doing CFD on their rotor shape. And initially, we were partnered with an electrostatic generator startup, C-Motive, to try and get a high torque, low speed generator. We've since our development timelines just didn't align, and so we've since moved to using off-the-shelf generators and gearboxes. And then the tethered turbine, it turns out, provides a lot of structural efficiency because there's no cantilevered load, so there's no big beams necessary. Everything is almost everything's in tension. The blades themselves are cantilevers, but beyond that, pretty much everything is in tension, which uses material very efficiently. And we can also scale the rotor independent of the rest of the system to match a particular resource. So if you have a fast resource or a slow resource, you can scale the rotor diameter up and down. There's some constraints. You still have to be in the torque speed envelope of the generator, but some good flexibility there. And then for OpEx, increasing that, both of these actually both reduce the cost of operating and maintaining and actually serve to increase the M1 parameter through increased capacity factor. But the idea is to deploy these systems from the shore, so you don't have any on-water infrastructure or equipment, and the debris resilience of the system should increase the uptime and capacity factor compared to other designs. And so on the bottom left is our initial schematic of an early design of a generator housing, flexible torque rope, and the rotor. And then on the right is a schematic of a potential way to deploy an array of these from the shore using a boom arm and cable. So we got final approval to start the work in July of 2021, and we raced to build a prototype and get it in the water before the river froze. And so we were out there in September of 2021 in the snow. Pretty miserable, but pretty simple system. You can see on the left, they took an early rotor design and just scaled it up kind of crudely, got it built. BladeRunner really focuses on the rotor technology, and UAF is really focused on just designing and building the generator housing. And so here we had a generator we had on hand. I think we got the gearbox, just a simple inline PTO, simple housing, rudimentary frame. And it was really good. We learned a lot. 3 months in, we had a lot of experience that we didn't have when the project started. We got initial data on the depth control of the rotor and that stability, and pretty dismal performance objectively, a peak CP of about 25% and a low tip speed ratio of 2. But I think anyone with experience would look at the blades and know that those are not going to be high performing blades. So the beauty of the Sharks program and our proposal was that we structured it so that every year, every season, we were coming back with an iteration of the prototype with improvements and changes based on the prior year. And so in 2022, we were back, improvements on the torsional cable, new nacelle and hub for the rotor. You can see the blade designs are much improved. They spent the whole winter doing CFD design. Built 2 rotors, one with a straight leading edge, one with a curved leading edge, in part to look at those trade-offs between efficiency and debris shedding. And ultimately, we saw a pretty similar efficiency between the two, and so the debris resiliency doesn't appear to be coming at a significant efficiency cost. To deal with the torque, so all of the torque is transmitted into this housing, and then the housing reacts to that torque based on its buoyancy in the water. So the generator housing rolls. And so we went from a flat bottom design to a catamaran to get more of the displacement outboard of the axis of rotation. And we offset in this bottom right, you can see that we used a belt with a speed increasing belt and then the generator and gearbox. And that shifted some of the mass to the opposite side of the generator housing to counteract that torque. And so, CP increased to 40%, tip speed ratio increased to 3.5. And then another part of this project that's been really great is it has some tech to market requirements. And we use that to actually engage with communities in Alaska and actually pay for travel to bring folks on site during testing. And so this particular year, we had folks from McGrath and Galena come visit, and kind of a two-way street, build awareness on their end of kind of what's coming down the pipeline technology-wise for river energy, and also just get their feedback and thoughts and input on the design and testing. And so it's been really valuable throughout the project. So another year, version 3.1, 2023, learned a really painful lesson. We had a torsional cable failure. And so basically we learned that in the cable, there's a transition from the bulk weave to the end termination where there's a stress concentration, as some of the fibers are embedded in epoxy and some are free to move. And so from that, we introduced a universal joint at that connection. So you can see that in the top right. More updates on the nacelle, increasing functionality, decreasing diameter, trying to streamline things. New fabrication techniques on the blades themselves. So BladeRunner's made huge improvements over the years in their ability to prototype and fabricate these blades, and really innovated in some of their fabrication techniques. Iteration of the generator housing made the catamarans actually asymmetric to push that buoyancy out even further. We offset the entire drive line all the way to the side, so getting rid of that belt, which proved to be a reliability headache, and getting just everything off center. And so actually the mooring line and the generator line are all off center in the housing. This year really focused on understanding depth control on the rotor, so a lot of changing out ballast, moving ballast around in the nacelle, and the blades were redesigned, more CFD optimization. CP rose to 44%, tip speed ratio around 4. And this year we had visits from folks from Napaimute and the Alaska Village Electric Cooperative, and then the Napaimute visit in particular I'll talk about later because we're now working with them on doing a pilot deployment this coming summer. So 2024 brought version 4, active buoyancy control in the nacelle, an early prototype. Another iteration of the generator housing, this time really focused on how the generator housing handles and how we can transport it and move it. And so we actually moved away from a catamaran and went to a flat bottom housing that's actually geometrically similar to a John boat. And this system was designed for 5 kilowatts of output at 2 meters per second, and demonstrated that, and is capable of 11 kilowatts at a higher flow speed, and folks can do the math there if they're curious. I think it's like 2.8 meters per second. So things getting sort of more and more sophisticated, but also more reliable as we go. And then 2025, this past summer, we'll call it version 4.1. So another iteration, or an iteration on the buoyancy control mechanism. And then we really had our eye this year on long-term deployment and on preparing for that Napaimute deployment where we're going to have unattended testing or unattended operations. So we built a lot of instrumentation into the housings. You can see there's an ADCP here on the back. We moved away from the torsional cable entirely to an aluminum drive shaft with U-joints both at the upstream and downstream end at the rotor. This system actually, or a few other things, you can see a Starlink. So this thing has its own satellite internet connection. It's got some resistors on deck, braking resistors if we lose the VFD, which I'll talk about a little bit in a few more slides. But this system actually ran unattended for 264 hours, so a little over, or just about 11 days of operation with no one on site, which was pretty exciting. But here's a video of it with the rotor deliberately operating at the surface. So the rotor operates fully submerged, but it's kind of boring to look at if you can't see the rotor spinning. So here's things humming along, and the fish crew downstream sampling for fish. And this is you can see the generator housing is kind of rolled to its port side. As the rotor torque increases, the generator housing will actually roll more to starboard. So kind of an overview of the performance improvements. Here's the CP tip speed ratio curves over the years, and oh, I should say here that all of this is really my perspective from the university side of things. Moriel at BladeRunner will probably have his own and perhaps more insightful perspectives on things, and so that could be maybe a future talk. But he was gracious enough to let me share a lot of these figures and photos. So they've really achieved some pretty significant performance improvements over these iterations, and not just increasing CP, but increasing tip speed ratio makes that conversion, the power takeoff, a much less challenging design problem. We have these high speed, low torque generators and this high torque, low speed rotor, and so the more we can bring those together, the less the requirements on the gearing side are. We've made a lot of minor reliability improvements over the years that really add up to something that can run for 11 days unattended. That the first year it seemed like every 20 or 30 minutes there was something we wanted to pull the system out of the water and fiddle with or check on. Buoyancy control, so being able to maintain that rotor depth where we want it over a wide range of inflow conditions. That also gives us curtailment options, the ability to surface or sink the rotor, or the ability to operate at a higher or lower tip speed ratio. And then, I already referenced unattended operations. So now I'll talk about our collaboration with NC State. And so this really came from the program director. The same program director that was running Sharks was also involved in some ARPA-E open projects, including this one at North Carolina State University. And I should have written down the lab, but it's Srijan, I'm going to mispronounce his last name, Lucic, I think Lucic. But they're developing something called the Micro C3 controller, which is an open source controller that's designed to really interact with a wide range of hardware that might be on a grid or microgrid. And so we've been working with them to actually make this system grid connectable. And so the early prototypes, we just had a diode bridge rectifier on the output of the permanent magnet generator, and then we just ran dissipated power into a DC load bank, and we could change that DC resistance to change the tip speed ratio that we were operating at. What NC State is letting us do is actually control a VFD, and so our servo motor generator in the generator housing is now pulling or pushing power onto a 450 or 480 volt bus. And then for microgrid applications, we're looking at using this multi-port power converter from a company called CET. And it basically has a bidirectional DC port that can talk to a battery or pull and push power from a battery. It can create the 450 volt bus for the VFD, which is again bidirectional, and it has a third port that is basically a DC dump load. And so this is all driven by the fact that NaPi-Mute does not have a three-phase distribution system. In most remote communities, there is a 40 volt distribution, and so you could connect the VFD directly to that. And so the Micro C3 is also able to do controls, and so we're implementing speed control through the VFD. And we're basically reading torque in real time and then controlling speed proportional to the square root of torque. And so in theory, that gives us tip speed ratio control over as velocity fluctuates. In reality, it's not perfectly linear, but it's something that works well for the range of inflow conditions we see, in any given testing period. And so this is just a view in the generator housing. The VFD is in there with their regenerative drive unit. We've got an onboard battery so that basically if we lose that 480 volt bus, the VFD goes offline and goes open circuit, and we would risk overspeeding the generator, over voltage, insulation failure. And so we have both a battery on board for powering all the communications and monitoring and instrumentation if we lose the bus. And we have some normally closed relays that are basically held open by that bus, but if the bus goes down, these relays close. And some DC resistors basically the generator gets shunted to these resistors, and it keeps the generator in a reasonable operating range in terms of torque and speed. On the outside, to prepare for these long duration testing at our test site, and then ultimately for a deployment in the Napaimute, we've got satellite internet, the Starlink antenna, we've got PoE cameras so we can remotely see what's going on. And basically the only connections to the system are a mooring line to carry the drag load and the electrical connection for the power export. And then, on board, we've got mooring line, load cell, we've got the ACEP, we've got inclinometers for pitch and roll. All the electrical signals are monitored. And then the control systems, any systems are logged as well. And so, what this looks like this summer, Moriel was able to sit in his office in Oregon and control his turbine remotely, see his dashboard with all his control parameters, and watch a live feed off the camera of the system deploying. So pretty exciting stuff for us, and something we hope to kind of make, run-of-the-mill in the future. So just a summary of, those 4 or 5 years of iterations. The rotor design itself has evolved. The methods of fabricating it have evolved. The depth control system has been invented and demonstrated and improved. Torque transmission, kind of testing the limits of this flexible cable, and then ultimately finding that a simpler aluminum shaft with U-joints seems to provide the debris, the compliance we need with much lower cost and higher reliability. Power takeoff, initially thinking it was going to be this complex, novel electrostatic generator, and now finding a pretty robust solution with just off-the-shelf servo motion control components. Electrical control and conversion, going from a very simple load bank and rectifier to now something that can connect to a 3-phase bus and can do more advanced control like this K-root T control. Housing designs, we sort of thought we were going increasingly in the catamaran direction, and then found that it was really a pain to deal with, and that something that fit on a normal John boat trailer might actually be advantageous. And deployment and retrieval. So I'll talk about that here next. So the shore-based deployment, 2022, we did a 40-foot proof of concept. So basically just this boom, aluminum boom, made to be lightweight and reasonably stiff. And then there's a cable that goes upstream that we can let out to kind of let this swing out into the current. And so kind of here's what it looks like. And what we found was that a spot that looked good at 40 feet actually didn't have much current. We actually weren't able to spin a rotor. And so we said, well, we'll make it bigger and get further out into the river. So the next year we came back with an 80-foot boom, and the water level was much higher. And what we learned was that the eddies get bigger when the water level is higher. And so even out at 80 feet, we had the rotor out there, but we really didn't generate any meaningful power. And so this idea kind of sat for a couple years, but now that we're going to Napaimute, the plan is to go with a shore-based deployment at their site. The other thing we get to do at the test site is debris testing. And so there's a certain amount of debris that comes through naturally, and that's great. A running tradition with the BladeRunner project has been that every Friday, the second after lunch, we go out there. We spend the week sort of sending the interns to collect debris of all shapes and sizes, and then we spend Friday afternoon introducing that debris to the system. It's always interesting, always fun. We haven't been able to break anything doing this. And then this is a clip I've shared before, but this was actually uncontrolled debris. So this was an actual tree that came through, rolled under the barge, actually damaged our ACEP mount on the barge, but we have a GoPro running at like 1 frame per second. So I'm going to play this, and you can kind of see the generator housing bump, and then you'll see the log kind of move down the torsional cable. You'll see the torsional cable coming out of the water, and then you'll see the rotor hop up over the debris. So there's the tree, cables coming out of the water. Rotor is impacted, debris passes under the rotor. The rotor begins to spin again, and then beyond this, the rotor submerges again. So pretty cool to see that, a real impact like that. And both something that you can only really get in field testing and a validation that this compliance on the rotor pays dividends on the debris front. So some general reflections, and again, from my point of view, things that have definitely been successes. The ARPA-E approach and mindset has really allowed us to take some risks and innovate quickly. And we've had all sorts of things we've done with their money that didn't work, and they've had a really good appetite for that. And as long as we close the loop and talk about them, it's been a really positive experience. Getting to iterate in hardware and field testing, I think, is invaluable. There's a lot that can be done just looking at the CAD models and talking through things. And I think it's always going to be a challenge of where to draw that line. How much can you figure out sort of cheaply in software, and then how much do you kind of have to learn in real life? Key takeaway we've had is that simplicity is really correlated with reliability and efficiency. And so the fewer steps in your chain, the fewer losses you have, and the fewer places for failure. But we have had to add complexity in some cases, and so we've really tried to do that only as necessary. And often we'll add complexity as an easy solution, and then try and reduce complexity. We'll solve a problem with complexity, and then we'll refine that solution with a move back towards simplicity. And then another big thing that I think has been successful is that we've really divided responsibilities. BladeRunner's been able to focus on their core technology, and UAF is focused on sort of the periphery of, how does this thing get in and out of the water? How do we do the field testing? How do we design and build the generator housing with, largely off-the-shelf stuff? And so it's just been key to communicate those interfaces between, different aspects of the design. And this is continued with NC State and where our systems interface, and I'll talk about that next. Kind of how that's where that's going. So, or no, I guess I already talked about those slides. So lessons learned, like kind of more painful lessons learned, that seasonality here really drives the timeline, and so we've had to learn to be more and more proactive about what do we actually need to get done in November. Like everything can't just be done in April. Shipped up in May and tested in June. We really got to, use that whole off season to get things lined up. Setting reasonable expectations for field work. It's easy to say, oh, we got 5 days and we'll do this and this, and Monday we'll do this and it'll go perfectly. Tuesday we'll do these things. So it's good to have a plan if everything goes well, and then it's also good to schedule your high priority items first and have things that can fall back if they need. And then often we'll have BladeRunner up for 2 or 3 campaigns a summer, and so we'll have a week of testing, and then we'll have 3 or 4 weeks or 5 or 6 weeks to respond to anything that happened during that testing before we come back. Small things can be big problems if you just don't have the right size wrench or the right size bolts, or some wire breaks somewhere and you got to tear something apart to fix it. So, really sweating the small stuff and being kind of anal about, exactly what do you need, where do you need it, where is it really in that toolbox, or is it back in Fairbanks an hour, a 2-hour round trip drive away? And to steal a term from the environmental side, adaptive management. And I'll show some pictures here that, on the top left, it's snowy, it's cold, it's slippery. People are uncomfortable, a different set of expectations there than on a beautiful sunny day. The bottom picture, here clearly we got 3 folks working on 3 different problems at the same time, and we've got data coming in, clearly the turbines in the water. Whereas on the the top right, folks are really kind of focused in on the same thing, and just kind of knowing where you are in the process and what what people can and can't do all at once. And then in a best case, that bottom right picture, we're kind of just hanging out, watching data come in. Everyone's relaxed, things are going well. It's comfortable. We're in our shirt sleeves. It's a nice day. So next steps. So this project is ongoing both with NC State and with a separate plus up for commercialization. So we're working on a pilot deployment with Napaimute. We're basically going to take the system we've already tested, this 4.1 system, and try and take it out to Napaimute, deploy it, integrate it into their grid using NC State's system, and learn some lessons. A real key thing there is identifying a partner who has a risk appetite and an attitude that aligns with R&D. And so we've really found that with Native Village and Napaimute and the folks we're working with there. And then on the BladeRunner specific side, we're working through a plus up to move towards commercialization. So moving from a prototype, a one-off design to something that's more production ready to do, small runs of multiple units. So modularizing, simplifying, ruggedizing components. And we're hoping to do some winter and summer applications in the next 18 months. So a few slides on the Napaimute pilot project, and then I think we can get into some Q&A. So these are just some photos from Napaimute in terms of motivations. So Napaimute is a summer-only community currently, but there really is a strong interest in making that community year-round again, and energy is a huge part of that. But mainly right now it exists as a subsistence hub in the summertime. People come to fish, people come to gather berries. In the fall, there's moose hunting. So on the left here's a Jack King, so it's a young king salmon, small king salmon coming out of their fish wheel just upstream of town. In the middle, in town, there's chest freezers for preserving food. They do smoke salmon and more traditional ways of preservation, but freezers sure are nice for keeping food from spoiling, and a Starlink router there as well. And so energy enables communication and connectivity. And on the right is the gas pump in Antioch, which is the major town downstream, and that's $150 for 16 gallons of gas. $9.30 a gallon. So running generators is hard to justify on a year-round basis. And so we've been out there. We've done some resource assessments, some ACEP transects, and we've got some really nice velocities over 2.5 meters per second in this north channel, which is great because most boat traffic and barge traffic is through the south channel, which is wider and deeper. The community here is on the north bank, on the left side of the picture. Current is flowing right to left, east to west in this image. And so the hope is to deploy off of this north bank in this north channel and run power along the bank into shore. And so here's what NC State's implementation looks like in Napaimute. So their micro C3 nodes will be connected to the BladeRunner turbine, controlling the generator and VFD, to the multi-port power converter, controlling its set points and power flows, monitoring the battery itself, and then talking to Napaimute's split phase hybrid inverter. And so this system stands up their 240 volt split phase distribution and accepts power from both their stationary generator and their solar arrays, and can charge the battery. And so the idea is that we're connecting to the DC bus of the battery in parallel with their system, so we can come on and offline as needed without interrupting their energy system. And then finally, a plug, unrelated or somewhat related, we are running a short course this summer, Hydrokinetics in a week, fieldwork and fish sampling on the Tanana River. This is targeting graduate students and highly interested juniors and seniors, undergrads. Travel and lodging are covered. There's a link and a QR code for the application for that, and applications are open. I forget when they close. I think in a month or so. So last week of July this summer in Fairbanks and Nenana. So that is all I've got, and happy to take questions on any and all of this.
So one question that popped up in the chat, I'm curious what kind of environmental monitoring you have to do in order to operate.
Yep, that is a good question. So we are permitted with Alaska Department of Fish and Game, and so we have a habitat use permit, and so that allows us to operate in fish habitat. And then the College of Fisheries and Ocean Sciences has a aquatic resource permit, so that enables them to take fish, sample fish. And we're really fortunate in Alaska that, years and years ago when they were approached about the idea of this test site, they said, cool, that sounds really interesting. We want to know, we want to know, we want to learn. And so basically the condition of the permit is that we need to be sampling representatively when we're doing testing. And so every year there's a report that gets filed. It should be public. If you're curious about those, I can help you find them or direct you to Andy Seitz is the PI on the fisheries side. But they do a mix. They sample, and they have their own ongoing research separate from this. But anytime we have a turbine in the water, they're sampling downstream of the turbine with some kind of method.